Hello ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over Half-Life, so make sure you follow along in your notes. If you have any particular questions, make sure you ask me tomorrow. So, the question that we're going to be looking at is how quickly does radioactive decay take? So how much time does it take for something like radioactive decay to happen? So we talked about three types already, alpha, beta, and gamma, but now we have to talk about this concept called half-life. Now the symbol for half-life is T with a 1/2 subscript. And what that tells you is the amount of time it takes for half of substance to decay. Now, why is that so important? Well, it's important because we see the same repeating pattern over and over and over again. So, for example, let's take a look at this graph. So at time 0, I have 1,000,000 of something. Okay, and so that would be like right here on my graph. After one half-life, I literally have half left. So I now have 500,000, which would be right here. After a second half-life, I have a quarter, and so that would be 250. After 3, I have an eighth, that'd be 125. And the pattern repeats over and over and over and over again. And so that's how we get this sort of pattern on our graph. Now, what is that pattern? It is an exponentially decreasing function. And that's very important because we always get the same shape whenever we're dealing with half-life questions. So how exactly do we calculate half-life? Well, this is our half-life equation, and yes, you need to memorize that and to know it. And it looks a little bit more complicated than it actually is, but there are really only three key variables in this equation. And just like any algebraic equation, if you know two of them, you can solve for the missing third. Okay? So n, what does n represent? N represents the amount of substance that is remaining. So amount of remaining substance. So in other words, it's how much you have left after you've actually done your radioactive decay. That's the amount remaining. N sub O, that is our initial amount. It's what you start with. And so it is what we start all of our problems off with. T to the 1/2, that is the number of half-lives. Okay, it's not the half-life itself, but it's as if we are counting half-lives. So on our graph, if we're going back to that, right here, notice you have time 0, then you have half-life, that would be like one half-life, then you have 2 half-lives, and 3, and 4, and 5, and 6, and 7, and 8, and 9, and 10. Now half-lives can be different amounts. They can be in years, they can be in billions of years, they can be in seconds. There are many different sort of ways of counting the number of half-lives, okay? So that's why we go off of just how many there are rather than just, a unit like seconds or minutes or hours or years. So now let's actually use this information about half-life to solve some problems. And so here's the thing about half-life questions. They all use the same formula. So n equals n sub O times 1/2. I'm just going to put 0.5 and then T sub 1/2 like that. Okay, and so that's our equation. Remember, each one of these stands for something different. So each one of these is a different variable. So I just have to figure out where to plug them in. Bandages can be sterilized using cobalt-60, which has a half-life of 5.27 years. That should say has. How much of a 10 milligram sample of cobalt-60 is left after one half-life? What about 2 half-lives? What about 3 half-lives? So it's kind of nice and easy. I'm given lots of information. It's telling me the half-life is 5.27 years. Remember, the half-life can be any length of time. It doesn't matter what that is because we're counting how many half-lives there are. How much of a 10 milligram sample of cobalt-60 is left? So that piece of information right there, it's giving me my n sub O. It's giving me my initial amount that I started with. So I can plug in 10. I also need to have my half. And it says how many half-lives? 1 half-life. So I would say to the 1 power. And that will give me, after 1 half-life, how much I have left. So in your calculator, 10 times 0.5 raised to the 1 power. And so that is literally just a half. And so we end up with 5 milligrams as a result. That's 1 half-life. Now what about 2 half-lives? All right, I'll do the same thing. Just like this. Trying to keep my colors consistent, raised to the 2 power. Why? because it says after 2 half-lives instead of 1. And so yes, it goes down by half, so 2.5 milligrams, just like that. And then I wonder if I can squeeze this in. But just like the last one, I now do 0.5 raised to the third, and that's the same as taking an eighth. So I end up with 1.25 milligrams. And from that, you can start to see where that graph comes from. So I'm going to try to draw this little graph in the corner. It's not going to look very pretty or anything. But if I started at 10, let's say, at time 0, so somewhere up here on the y, then I would go to 5 after 1 half-life, and then I would go to 2.5 after, a second half-life, and then I would go to 1.25. And you can start to see that curve appearing, which is our half-life curve. Alright, so let's try to solve another one. Krypton 85 has a half-life of 11 years. How much of a 2,000 milligram sample would be left after 33 years? Again, given lots of information, but I always have to use the same exact equation. Okay, and so my equation looks like this. That's a T. So I have to start getting information from this. So it says how much would be left after, a certain length of time. So again, I'm given my n sub 0. So that means I can plug in, sort of 2,000 as my n sub 0. I'm being asked again, how much would be left? So I don't know what that would be. And then I have to figure out the number of half-lives. Now, the big mistake that people would make would be, they start to plug in 11 or 33 or something like that. Here's the problem. I have to figure out the number of half-lives that have passed. So if the half-life of krypton is 11 years, and I'm asking how much would be left after 33 years, how many half-lives, remember we're looking at the number of half-lives, have passed in that time? Obviously, 3. If you don't know that, 33 divided by 11 is 3. Now, where did that come from? Well, it came directly from the problem. If the half-life's 11, how much would be left after 33 years? So I would need to plug in 3 as my half-life number up at the top. So in my calculator, I would put 2,000 times 0.5 raised to the third power. When you do that, you get 250 milligrams. That's how much would be left. Why does that make sense? If I start with 2,000, after 1 half-life, I would have 1,000 left. After 2 half-lives, I would have 500 left. After 3 half-lives, I would have 250 milligrams left. Now here's a very good question. If 5 half-lives leaves us with 3.50 milligrams of a strontium-90 sample, then how much was present at the beginning? So now I'm given a different set of information, but I still use the same exact formula as before. So that's my half-life formula. 5 half-lives have passed. That's a nice piece of information that I can start to plug in. I can plug that in right here because it's giving me a number of half-lives. If I have 3.5 milligrams left, how much was present at the beginning? So I am being asked to find this. I don't know how much I started with. What I do know is how much I have right now. I have 3.50 milligrams, and I would like to know what this number is, n sub 0. But I have also the rest of this to plug in. So you need to do some manipulation in your calculator in order to get this to work. Okay? So I have 3.50, and I need to get my n sub 0 by itself. So I need to divide by half raised to the 5th power. Half raised to the 5th power. Now think this through logically. I'm going to erase this now on this side. But think this through logically. So is the number that I get going to be a big number, or is it going to be a small number? So I'm taking a smaller number, 3.50. I'm dividing by a small number. When you divide by a small number, what happens? Your answer gets bigger. And so I should end up with a number bigger than 3.50. If I've been going through decay, I would have started with a lot more stuff. After 5 half-lives, I'm not going to have as much stuff. So make sure your number actually makes sense. If you plug in something blindly in your calculator and just put out an answer, that's not really helping you. So what do I get? I get 112 milligrams. That's what I started with. And so I could actually do this, and actually I don't have this out, so I'm going to have to get my calculator. But I could do this, by just dividing by a half every single time. So after one half-life, how much is left? So I start with 112, I divide that by 2, I get 56. So this is after one half-life, I get 56. Then after a second half-life, I get 28. After a third half-life, I get 14. After another half-life, I get 7. And then after my last half-life, I get 3.5. That's my progression, okay? So I started with one half-life here, 2, 3, 4, and 5. And guess what? That's correct. 3.50 is what I was left with by the time I was done with my decays. And so again, you should start to see, if you haven't already, this pattern. At time 0, I started with 112 milligrams. Then after one half-life, I ended up with 56. Then I ended up with 28. Then I ended up with 14. Then I ended up with 7. Then I ended up with 3.5. You can start to see the curve appearing. And that's literally it for half-life. So again, if you have questions, make sure you ask.